Hello and welcome to the 8th lecture of Analog Integrated Circuit Design. At the end of the previous class, we summarized what happens in a negative feedback amplifier with delay. We will just go through that again quickly. What we saw was that small delays in the negative feedback amplifier actually speed up the response, so it is beneficial, but this happens for up to tau equals 1 by E, approximately 0.36 times the time constant. This should be 1 by 2.718, not 2.718. Up to this value of delay, you will actually speed up the response compared to not having any delay, and this gives you the fastest response without having an overshoot. And if the delay is between 1 by E and pi by 2, that is 1 by E times the time constant and pi by 2 times the time constant, you get a stable response but with ringing. And for tau greater than pi by 2, about 1.5 times the time constant, the response is unstable, that is even without an input you will end up with an output. And in practice you cannot have a lot of ringing, so you have to limit the value of tau to under 0.5, that is half the time constant of the system. What we will do today is to look at how a delay comes about in a real system, because in a real system we will not have an ideal delay as we have been assuming so far. That was just a model for any delay that may come. In a real system, what happens is you will have parasitic poles and zeros in the frequency response at different points of the loop. We will see how they will equivalently contribute to a delay and what to do about it. To do this, we have to first look at how we can realize the negative feedback system that we have. So, the essential component of the negative feedback system is taking the difference between the input and some feedback quantity and integrating the difference, and you drive the output in a way that the difference is minimized. That is the essence of negative feedback. So, every negative feedback system needs to have a way to take some difference and way to integrate the difference. Now, because this is so widely used, this taking of the difference and the integration is integrated into a single block, and it is a very familiar block, and this is known as the operational amplifier or op amp for short. So, essentially an op amp is a block that takes the difference and integrates it, where these terminals correspond to these. Okay. So, this is what an op amp is. It is a block that takes the difference between two quantities and integrates the difference, and you can very easily see that the op amp can be wired up to make the negative feedback amplifier that we have. If I have to use the op amp in this diagram, what I will do is I will apply Vi to A, the plus terminal of the op amp, and the output is divided using the voltage divider, and the output of the voltage divider forms the other input to the op amp. The difference between these two is integrated to drive V naught, and many of you may be familiar with this circuit as the classical non-inverting amplifier. Okay. So, we have to realize a block that makes the we have to realize a block that takes the difference and then integrates the difference. Now, if you look at the circuit elements that we have resistors, capacitors and inductors, and we can also make a variety of control sources using transistors. This you are already familiar with. You have a common source amplifier, common gate and common drain, and some of them are useful as voltage controlled voltage sources and some of them as current controlled current sources and so on. And the transistor by itself acts as a voltage controlled current source. Either the MOS transistor or the bipolar junction transistor acts as a voltage controlled current source. Okay. But here what we need is integration, that is integration with respect to time, and of all the elements we know, the inductor and capacitor are elements that do integration. The inductor integrates the voltage across it to give you the current through the inductor. The capacitor integrates the current through it to give you the voltage across the capacitor. Now, inductors are rather bulky, and if you try to realize the kind of integrators that you want in an op amp using inductors, it will become very large and they are impractical to realize. So, we are left with only one alternative, that is to use a capacitor to get the function of integration. So, a capacitor which has a voltage V c across it and a current I c through it obeys the relationship I c is C times the derivative of the voltage, or V c is 1 over C integral of the current. Now, the difference is available as a voltage. This is a difference voltage V e, and this is what has to be integrated, but the capacitor integrates a current. So, we first have to convert the difference voltage. I will call this V a and V b, and I have to integrate the difference between V a and V b. So, I first use a voltage controlled current source which gives a current proportional to V a minus V b, and this current flows through a capacitor C to result in a voltage which is 1 over C integral of G m times V a minus V b with respect to time. Okay. Now, this particular block, it is a voltage controlled current source, and in integrated circuit design a different symbol is used for it for the same function. We use a symbol that is somewhat similar to that of an op amp. Okay. And this symbol means a voltage controlled current source, and you typically write the value of the proportionality constant next to the voltage next to the symbol, and this means that a current G m times V a minus V b will be forced out of this block. So, this is the voltage controlled current source or a trans conductor, okay, and this value G m is the transconductance of this transconductor. Okay. Now, I will rewrite my integrator using this symbol. So, now we know that the voltage at the output or the voltage across the capacitor is some constant times integral of V a minus V b with respect to time. Now, we can try using this in our amplifier. Earlier we wrote down the picture of the amplifier, which is like this, okay, where this op amp is realized using this circuit. we can try to do this. So, think about this circuit for a moment and see if it works. You will immediately see a big problem here. The current Gm times Va minus Vb was supposed to flow through the capacitor, but the moment you connect these resistances, some of that current will flow through the resistances and the integration function is not exactly what you wanted. Okay. To prevent this, we have to make sure that no current is drawn from this point and all of the current from the transconductor goes into the capacitor. Okay. And to do that, we will use a voltage controlled voltage source or a voltage buffer. Okay. So, finally, the picture of the op amp is as follows. We have the transconductor which drives its output current into a capacitor, and to avoid drawing any further current from this, we use a voltage buffer. This means that the voltage here is the same as the voltage there, but the input resistance of this block is infinity and the output resistance is 0. So, this block does not draw any current from the capacitor. At the same time, it can provide any current that is required from its output. So, this now is the equivalent circuit of the op amp. This is a way in which an op amp can be realized. Usually, there is a lot more detailed circuitry inside, but for now this will do. Okay. Okay. If you look at the transfer function of the op amp by itself, that is the transfer function of this block, okay, the output voltage of the op amp is given by Gm by C integral Va minus Vb with respect to time, and what we wanted was for it to be omega u integral Va minus Vb with respect to time. Now, if you just match the terms, you will immediately see that the unity gain frequency of the integrator omega u is Gm, the value of the transconductance that you use, divided by C, the value of the integrating capacitor that you use. Okay. So, omega u is Gm by C. So, this is exactly equivalent to the amplifier that we had earlier using the integrator, and we can do our analysis with this. All you have to do is to substitute omega u by its value, which is Gm by C. Okay. So, now what can happen here that can give you delay? So, there are several possibilities. So, first of all, we have the voltage buffer, and ideally the transfer function of this it is 1, and in reality it could have some poles and zeros. Okay. It will be 1 times 1 plus S by Z1, and it could have multiple zeros, also it could have multiple poles. Okay. Now, the exact transfer function depends on the details of the circuit that is used to implement the buffer. Similarly, the transconductance, the transconductor has its I out by V in, where V in refers to the difference voltage V A minus V B. Okay. This is V A and that is V B. So, I out my V A minus V B should be a real number G M, but what can happen is, depending on how complicated a circuit you use to realize the transconductor, this could also have extra poles and zeros. Okay. So, I am just showing the transfer functions in a general form. There can be extra poles in the transconductor, there can be extra poles in the buffer. Also, first of all, the reason for getting extra poles in any system is that there are parasitic capacitances from every node of the circuit to ground. Okay. So, for instance, here ideally there is nothing, but in reality there will be a capacitor. So, let me call that Cp with respect to ground, Cp between that point and ground. Now, what happens because of this? Let us examine the voltage divider by itself. If I have V naught here, I will get V naught divided by K. Okay. But in reality, I have this. In addition to that, I have, let us say, a single parasitic capacitor Cp over there. If I have V naught here, what comes out here? You can again use the voltage divider formula to get the result. The voltage that comes there is V naught times the impedance of this part of the circuit, and the impedance of this part of the circuit is R times 1 by SCP by R plus 1 by SCP, that is a parallel combination of R and 1 by SCP, and this is equal to R by 1 plus SCP R. Okay. So, this is a useful result to remember, that if you have a resistance and a capacitance in parallel, the combined impedance is given by this formula, okay, R by 1 plus SCR. What it means is that at low frequencies, at DC the capacitor is an open circuit, it does not come into picture. So, at DC the impedance has to be R, and that we see is the case because we have R divided by 1 plus SCPR, and for DC S is 0. So, the impedance of this combination at DC is R, and at low frequencies, when the current through the capacitor is negligible, the impedance is still R. This means that the second term in the denominator is negligible compared to 1. At very high frequencies, the capacitor tends to act like a short circuit, and in fact, most of the current goes through the capacitor instead of the resistor. Again, if you now imagine that the second term in the denominator here is much more than the first term, we will get approximately R by SCPR or 1 by SCP. So, at high frequencies you see only the capacitor Cp. Okay. So, this expression makes sense, and as I mentioned in the introductory lecture, whenever you analyze a circuit, it is important to interpret the results and make sure that they make intuitive sense. What the expression is saying is that at low frequencies the impedance will be R, and at high frequencies the impedance will be Cp. As you well know, when you have a parallel combination, the impedance is dominated by the lowest impedance. At low frequencies the impedance of the capacitor is very high, it does not come into picture, but at high frequencies the impedance of the capacitor is very low, and that is what dominates the picture. Okay. Coming back to the transfer function of the voltage divider, I have R by 1 plus SCPR, that is the impedance of the lower part, divided by R by 1 plus SCPR plus K minus 1 times R. Okay. Let me erase this part of it. and this if I simplify I will get R divided by k times R plus k minus 1 SCP R square, okay, and R cancels out to give you one by k plus k minus 1 times SCP times R, okay. And this I will rewrite by pulling out 1 by k outside, okay. So, what this is saying is you have 1 by k, which is the value that you expect, times 1 divided by some term that contains a pole, okay, some term that contains S. So, if you look at this part of the function is 1 at DC when S equals 0, and it keeps decreasing as S increases, as omega increases, okay. At very high frequencies, what happens is, because of this capacitor Cp which acts like a short circuit, even if you apply a voltage here at a high, if the voltage has a high frequency component, that component will be shorted out to ground and you will see nothing at the output. So, this is the transfer function of the voltage divider, and I will rewrite this as 1 by k, which is the ideal value, times some transfer function that contains a single pole, okay. I will denote that P2. In this case, P2 happens to be k minus 1 by k times, sorry about that, k by k minus 1 times 1 by Cp R, okay. So, in the voltage divider also you can have a pole, and we will see soon that a pole acts like a delay, okay. So, to summarize, the voltage divider has a pole due to the parasitic capacitance Cp, okay. So, every part of the circuit, the transconductor, the voltage buffer and the voltage divider can have extra pole and also extra zeros. For the voltage divider, I have only illustrated an extra pole, but it is possible to have a 0 if there is a capacitance between this point and that point, okay. So, in general you will not have only the transfer function that you want, you will also have extra poles and zeros, and that is how delays come into the system, that is how all this non-ideality comes into the system, okay. Now, why is this equivalent to a delay? We will later do the quantitative analysis and see how the equivalence is produced, but for now just note that if you apply a step to V naught and initially the voltage here is 0, what happens is the capacitor holds the voltage at 0, it does not rise up beyond 0. So, effectively even though you apply an input step, the output is not a step, for some time it will remain at 0 and it slowly increases. So, that is equivalent to a delay. Basically the capacitor needs time to charge, it takes some time for the voltage across the capacitor to change, and that manifests itself as a delay in the system, okay. So, in general we can have additional poles and zeros in the transfer function, that is what it means, okay. So, while modeling the delay, I will use the Laplace transform here. While modeling the delay, what I had done was to insert an ideal delay e raised to minus s times T d, okay. Now, what I have to do is not this ideal delay, but some extra factor that has all kinds of poles and zeros. Now, as I mentioned earlier, the poles and zeros come inside the realization of the integrator and in the divider and so on. But we can club the effect of all of that into poles and zeros in the feedback path. Okay. So, in general, in the feedback path we can have 1 plus S by Z1, 1 plus S by Z2 etcetera divided by 1 plus S by P1, P2 and similar other factors. Okay. So, the bottom line is that there are extra poles and zeros in the system, and these poles and zeros can be in any part of the system, that is the transconductor, the buffer or even the voltage divider. But for the sake of convenience in analysis, we will club all of that into a set of poles and zeros in the feedback path. Okay. Okay. We can equivalently model the same using extra poles and zeros in the forward path as well. Okay. Because what we are looking for is the effect of the poles and zeros in general, okay, in general terms, and we can do it also in the forward path like that. Okay. So, for the sake of convenience, I will use this particular model, but you will reach the same conclusions whether you use that one or the other one. Okay. So, I will model all the extra poles and zeros in the forward path, and also I do not want to make my life so complicated that I cannot even solve the problem. So, first what I will do is I will assume a single extra pole in the forward path, then we will assume 2 extra poles, and then we will draw conclusions when we have multiple extra poles and zeros in the forward path. Okay. I have the integration, and let us say I have one extra pole. So, now what I can do is I can calculate V naught by V I for this case and see what happens. Okay. The way to calculate V naught by V I is like we have been doing all along. The voltage divider gives an output V naught by K, and I have to take the difference V I minus V naught by K. Okay. So, that is the voltage here, and clearly V E times the transfer function of this whole thing equals V naught. So, this voltage times omega u by S 1 by 1 plus S by P 2 equals V naught. Okay. and I will just rewrite this as I get this by moving this part to the right hand side. I also take this part and move it to the right hand side. Okay. So, V naught by V I turns out to be 1 by 1 over k plus s by omega u plus s square by P 2, which can be rewritten by pulling k outside. S square k by omega u times P 2. Okay. So, I have removed k outside because that is the ideal gain of the amplifier, and we see that the DC picture is not affected by the addition of the pole, and this is what you expect. You expect that the pole gives you a delay and something happens at high frequencies, but as far as DC is concerned, the DC gain of this block is unity. So, nothing happens at DC that is different from what was happening before. The DC gain of this path is still infinite, and finally, you will get a DC gain for the overall system that is equal to k. Okay. And that you can see here, if you substitute s equal to 0, you will get this function to be equal to k. Okay. So, rewriting this again, V naught by V I is the ideal gain k times 1 plus 1 by 1 plus s times k by omega u plus s square times k by omega u times P 2, which I will rewrite in the standard form for second order systems by multiplying both the numerator and denominator by omega u P 2 by k. The reason to write it like this is that you are already familiar with second order systems. You have analyzed the spring mass system and the LC system and know a lot about it. So, we will reduce it to a similar form that you are familiar and then see how the system behaves. Okay. Now, the second order system is characterized by its natural frequency and the damping factor. The natural frequency is usually denoted by omega n and the damping factor is zeta, and for these values the denominator should be s square plus 2 zeta omega n times s plus omega n square. Okay. If the denominator is of this form, this is omega n square and the coefficient of s is 2 zeta omega n, the coefficient of s square is 1. Now, by matching the terms between the denominator that we have and the denominator here, we can find out the value of omega n and the damping factor zeta. So, omega n comes out to be square root of omega u times P 2 divided by k, and zeta turns out to be P 2 divided by 2 divided by omega n, which is omega u P 2 divided by k. Okay. And I will write this as half square root of P 2 divided by square root of omega u by k. Okay. Now, if you know the damping factor and the natural frequency of a second order system, you can make statements about the kind of step response it is going to have. Okay. You know that if the damping factor is much more than 1, then the step response looked like the step response of a first order system, and if the damping factor is much less than 1, there will be sinusoidal ringing in the step response. The damping factor characterizes the step response and tells you whether the step response is over damped, critically damped or under damped. So, a negative feedback amplifier with an extra pole in the forward path. This has a second order transfer function whose DC value is k, as you expect. It is the ideal value, and the natural frequency of this is square root of P2 times omega u by k, and the damping factor is half the ratio of P2 by omega u by k and the square root of the whole thing. Okay. Now, if you plot the step response of a system like this, response of the system to a unit step. So, let us say the input has a unit step. Now, what will happen after a long time, the output will be equal to the DC gain of the system times the input voltage. So, after a long time, the output is going to reach k volts, because the input is 1 volt, the output is going to reach k volts after a while. Now, exactly how it gets there is determined by the damping factor. If the damping factor is much more than 1, then you get a very slow sluggish response like that, and if the damping factor is much less than 1, you will get a response that overshoots and undershoots and rings a lot and goes that way. Okay. This is what is known as an underdamped response, and if the damping factor equals 1, you get the fastest possible response without overshooting, and this is equivalent to a critically damped response. So, what we would like to have is usually the critical damped response or maybe a slightly under damped response, so there is very little overshoot. Normally, you would not like to have something that is shown here which has a lot of ringing. You would like to have just a little overshoot, if at all there is some. Okay. So, this is acceptable if it starts off like that, but certainly something like this that rings many times is not acceptable. Okay. Now, if you recall the analysis we did with the delay in the feedback loop, we saw that we had a similar phenomenon. For small values of delay, the response actually speeded up. That is like saying for modest values of damping factor which are greater than 1, the response actually speeds up. If the damping factor is much more than 1, the response is rather slow, and if the damping factor approaches 1, the response becomes faster and faster, and the response at a damping factor of 1 seems to be similar to the response for the delay being 1 by E, the normalized delay being 1 by E. Okay. That is critically damped, that is, it is the fastest response you can get without overshooting. Now, damping factor values that are much less than 1 seem to produce responses that are similar to when the delay is much more than 1 by E. You start to get ringing and overshoot and so on. Okay. What we will do next is to relate these two and see how the delay comes about because of the extra pole. Okay. The desired response is usually critically damped or slightly under damped. Okay. So, this is the kind of response that we are looking for. So, first let us calculate the value of the parasitic poles that are permissible to have this. Okay. Let us say I want to have a critically damped system, that is I would like to have zeta equal to 1.0. Okay. So, this means that zeta, which is half of square root of P2 by omega u by k, this should be 1.0. Okay. And from this you see that P2 has to be equal to 4 times omega u by k. Now, we also know that we get an underdamped response if zeta is much less than 1. That means that if P2 is much smaller than 4 times omega u by k, you can work out the inequality from this formula. If P2 is much smaller than 4 times omega u by k, you will end up with a severely underdamped response. So, you would like to keep P2 somewhere in this range where you will get either critical damping or a slight underdamping, but certainly not a severe underdamping. Okay. So, you can associate these values. Zeta equal to 1 is roughly like Td being 1 over E k by omega u. Okay. And zeta equal to 1 corresponds to P2 being 4 times omega u by k. Okay. We see that we can have high frequency poles, that is not per se a problem. If you look at this particular polynomial, the denominator has coefficients which are always positive. So, that means that the system is always stable. The roots of the denominator will always be in the left half plane, which means that the natural response dies out after some time. So, the system is unconditionally stable. You can have any value of P2, the system is still stable, but the problem is that if the second pole happens to be at a very low frequency, okay, that is if P2 is much smaller than 4 times omega u by k, you will get a severely underdamped response because the damping factor zeta becomes much smaller than 1. Okay. So, the summary of the system with the one extra pole is that you can have the pole, it does not cause instability, but it can cause severe underdamping. Okay. What we will do next? What we will do next is to extend this analysis to higher order systems. Now, as we go to higher and higher orders, the analysis becomes more and more complicated because you will have more complicated polynomials. What we will do is we will have, let us say, 2 extra poles at an identical location, then 3 extra poles and see what happens. But before we do that, let us look at what happens to the time domain response when you have an extra pole. Okay. This is the system which by now is very familiar. Now, I said earlier that to quantify the amount of negative feedback, you use the term loop gain, which is you set the input to 0, you break the loop and you apply some test signal and see what comes back here. Okay. This is the loop gain that quantifies the amount of negative feedback, and if the amount of negative feedback is very large, the system behaves ideally as you expect. Okay, you would like to have as large a negative feedback as possible. Now, in this particular case, the loop gain is, if you apply V test here, V test times omega u by s comes there, and then that divided by k comes here, and negative of that comes there. Okay. And the minus sign is included in the definition of loop gain. So, L of s is defined to be minus V return by V test, okay, which happens to be omega u by s times k. Now, this is for the system without any extra pole. Okay. Now, if you have an extra pole here, it is very easy to analyze. We get an extra factor of 1 by 1 plus s by p 2 added on to our original loop gain. Okay. L of s will simply turn out to be omega u by s times k 1 by 1 plus s by p 2. Okay. This is with the extra pole. Okay. So, what we can do now is to compare the time domain responses of the loop gain and see how they behave. Okay. This is the loop gain with no extra pole, and here I will plot the unit step response of the loop gain. Okay. And the unit step response of this function is very easy. It is a ramp. This is time. The unit step response is a ramp, and the slope of the ramp is omega u by k. Okay. Now, let us say we have one extra pole, then the loop gain will be omega u by k divided by s 1 by 1 plus s by p 2. Okay. Now, to study the step response of this, we can expand this in a partial fraction. We can expand the loop gain in the partial fraction form. This can be rewritten as okay. So, you can verify for yourself that these coefficients satisfy the equation, okay, satisfy the expression for loop gain. Now, the reason to write it down as in the partial fraction expansion is, now the step response of the loop gain is the step response of the first part of it minus the step response of the second part of it. Okay. The step response of the first part we already know. It is a ramp whose slope is omega u by k, and the step response of the second part is the step response of a first order system, which has the form 1 minus exponential minus p 2 t. Okay. It has this particular shape, and because of this particular factor, the height of this will be omega u by k divided by P2, and the slope at the start will be exactly equal to omega u by k. Okay. So, that means that we have to subtract something like this from the black curve, and both of them have the same initial slope, and the height of this is omega u by k divided by P2. And if you take the difference between these, the starting slope will be 0 and then it builds up, and after a while there is a constant difference between the two curves, and the constant difference is omega u by k divided by P2, and you can also express it as a constant difference in the horizontal direction. Okay. And the difference in the horizontal direction is nothing but the difference in the vertical direction divided by the slope. So, the difference in the horizontal direction is nothing but 1 by P2. Okay. So, plotting it on this axis here, if I have an extra pole P2, I get a response which has some detail here which I am going to ignore for now, but in the long term is simply horizontally shifted compared to the ideal response, and the horizontal shift equals 1 by P2. So, approximately speaking, the step response with the extra pole is delayed compared to the one without the pole by an amount 1 by P2. So, it is no surprise that the results when you have an extra pole look similar to results when you had the ideal delay. We also saw that if the delay becomes very large, that is if the value of 1 by P2 becomes very large or P2 becomes very small, you will have severe underdamping and severe ringing. Okay. So, having a pole is roughly equivalent to having the delay, and having multiple poles you will have delays due to each pole and you will have to add them up, and we will discuss that as we go on to higher order systems.